Hi students, welcome in chemistry classes. I am Priyanka Jain and you are watching videos of thermodynamics. In our last lecture, we have studied about internal energy, about heat capacity. Now there is one more important term that is called enthalpy. Enthalpy is actually one of the thermodynamic potential. It is a form of energy. Okay. Suppose we are taking a system that is undergoing a change from state A to state B. And this process is happening at constant pressure. Okay, it means system is going from state A to state B at constant pressure. Suppose this is our system. Okay, there is the piston. Okay, now what you are doing, you are changing it from state A to state B, but at constant pressure. Suppose here the expansion is happening, it means the volume is increasing. Okay, now the piston moves here. This is the state B, this is the state A, and this is the state B. So in this process there is a change in the volume. The volume is increasing. Now you can understand that work is being done. Okay, because there is an expansion process, so the work is being done. There is expansion work. So we can say the heat that we are supplying to the system is not only increasing its internal energy, but it is also used in doing the work. Okay, it means now the heat supplied to the system is not equal to its internal energy. It means we can say that the internal energy is less as compared to the change in the internal energy is less as compared to the heat given to the system, because the heat is now being utilized to do the expansion work. So this internal energy is not now equal to this heat supplied, but this heat supplied is actually equal to another important property that is called enthalpy. Now this heat supplied, as it is happening at the constant pressure, so we can write it QP. Okay, at constant pressure the heat supplied to the system is equal to another form of the energy that is called the enthalpy. Okay, it is denoted by the symbol H. Okay, suppose the work done is given by minus P VB minus VA. Okay, then del U, change in the internal energy, will be equal to Q minus P VB minus VA. Okay, here we can write UB minus UA. This is the change in the internal energy. This is equal to Q minus P VB minus VA. Or we can write UB plus P VB minus UA plus P VA is equal to Q. It means the change in this property UB plus PVP minus UA plus PVA is equal to heat supplied. There is a property that is equal to U plus PV. Okay, this property U plus PV is actually called the enthalpy of the system. Okay, this is called the enthalpy of the system. Enthalpy actually denotes the total energy stored in a system. Okay, this denotes the total energy stored in a system. So this is called enthalpy. As we know, this P, V, U, these all are the state functions because its value depends only upon the state. So this enthalpy is also a state function. Its value depends only upon the initial and the final state. It does not depend upon the path of the process. One more thing you should know, that enthalpy is an extensive property. Like other properties, this is also extensive property. It means its value depends upon the amount of the substance. Okay, its unit will also be the units of the energy. It means joule or kilojoule. Okay, as we know, H is equal to U plus PV, right? And we know PV is equal to nRT from the ideal gas equation. So we can write H is equal to U plus nRT, or we can write del H is equal to del U plus del NG RT. Here del Ng means the change in the amount of gas molecules, change in the number of moles of gas molecules. Okay, change in number of moles gaseous molecules. Here we does not consider the liquid or the solid state molecules. Okay, one more formula you can write here. Del H is equal to del U plus P2V2 minus P1V1. Okay, so sometimes you use this formula and sometimes you use this formula. Both the formulas are applicable. Now see, if we have to find out for the ideal gas, enthalpy for the ideal gas, how we can find out? See here, H is a function of T and P. Okay, we can write dH is equal to del H upon del T at constant P dt plus del H upon del P at constant T dP. Okay, now see here, this del H upon del T at constant P is equal to Cp. So we can write here Cp dt plus here del H upon del P at constant T dP. This is equal to dH. Now take its integration. So we are getting del H is equal to Cp dt plus integration of del H upon del P at constant T dP. As we know from the second equation of state, you have studied about second equation of state. I have told you about this equation. In our last lectures, we have studied about this. You can find its link in the description box. So from this equation, we know del H upon del P at constant T is equal to minus T del V upon del T at constant P plus V. Okay. Now see here. We know from the ideal gas equation PV is equal to nRT. Okay. So V will be equal to nRT upon P. So we can find value of del V upon del T at constant P. This will be equal to nR upon P. Right. So we can put this value here. Minus T nR upon P plus V. Okay, it means minus nRT upon P plus V. Okay, so this nRT, we know nRT is equal to PV. We can put here minus PV upon P plus V. Okay, so this will be equal to 0. It means del H upon del P at constant T is equal to 0. This term is equal to 0. So we can write del H is equal to Cp dt is equal to n integration of Cpm molar heat capacity at constant pressure dt, and this will be equal to n Cpm T2 minus T1. Okay, so you can use any of the formula when you need. Okay, this is the formula for the enthalpy for the ideal gas. If you have to find out the enthalpy for the van der Waals gases, actually in the case of van der Waals gases, I am not doing the full derivation because that does not need to you. Okay, and that is also given in the books. Okay, so you can watch the book of the K.L. Kapoor. That is a good book, but we are not using here. Okay, so see here, van der Waals gas equation is P plus an square upon V square, V minus NV is equal to RT. You can use this equation and you can find out del H upon del P at constant T is equal to N V minus 2A upon RT. Okay, so for van der Waals gas, del H will be equal to T2 to T1, integration between limits T2 to T1, CPdt plus integration on limits P2 to P1 and V minus 2A upon RT dP. So by using this formula, you can find out the enthalpy change for the van der Waals gases. Okay. So this is whole about the enthalpy change or enthalpy. Now the question is, what type of question are asked from this topic? Okay, so the questions that has been asked we will see in our next lectures. Okay, so watch our next videos. If you are liking the videos, please share these videos, please subscribe the channel, please comment, and please like. Thank you.